In this section, we will talk about the notation for the derivative. The derivative, like the addition operator or the subtraction, multiplication, or division operators, it's also an operator. It operates on functions. These four operators, they operate on numbers, they operate on functions, on matrices, on different kinds of entities. When we use the addition operator and add two numbers together, let's say 5 plus 4, we expect a number to come out as the result of the operation. This works because of the definition of the operator called the addition operator. It adds the operands, these two entities, or in this case numbers, with one another. The derivative, on the other hand, gives us, based on its definition, gives us the slope of a tangent line on a specific point on the curve of a function. This is the result of the operation when we operate with the derivative. The derivative operates on functions, meaning we differentiate a function, and the notation is like this. We take the derivative with respect to a variable, in this case x, of a function. This here is the derivative. We differentiate f of x with respect to x, and the result of this operation will give me the slope, will give me this thing here, the slope of a tangent line on a specific point on the curve of a function. To get an idea, f of x has a curve representing it. Let's say this is the curve of f of x. And this operation, the derivative, taking the derivative with respect to x, will give me the slope of a tangent line at a point, let's say this point P, will give me the slope of this line. Now more on the notation. We differentiate with respect to a variable. This variable can be anything. In this case, it's x. We can also differentiate with respect to y, with respect to u, with respect to any variable. Most commonly x. We differentiate a function, f of x. You will also see y's, where y is a function of f of x. So you can just plug in f of x here. We'll also see how the derivative shows us the rate of change of a function with respect to a variable. This thing here shows us how f of x changes when we change x. So the rate of change of f of x with respect to x, if we wanted to find the rate of change of f of x with respect to y, for example, we just take the derivative of f of x with respect to y. If we wanted to find the rate of change of f of x with respect to u, we'll just do this. In this case, we take or we differentiate f of x with respect to u. But in this case, f of x is a function of x. So most commonly you will see that we differentiate f of x with respect to x and f of y with respect to y, because we want to see how f of x changes if we changed f of x. If we changed x. A side note here, dx means a little bit of x. So we can think of this division as a little bit of f of x over a little bit of x. So we are seeing how a little bit of f of x changes when we change a little bit of x. Maybe y was a function of multiple variables, f of x and y and z. And we wanted to see how this function changes with respect to x. We'll just differentiate it with respect to x. So to summarize, dx means to differentiate with respect to x. dy dx means to differentiate y with respect to x, and y is a function. The result of this operation, differentiation, will give me the slope of a tangent line on a specific point on the curve of a function. So a function has a curve, and the differentiation will give me the slope of a tangent line. Differentiation will also help me find the rate of change of a function with respect to a variable, how y changes if I changed x, and how a function might change if I change any variable, be it x, y, or z, or any other variable.